Hello everyone, my name is Ibo P. I'm a PhD candidate at the University of Michigan. I'll be presenting our paper on internet load balancing. Due to load balancing, there could be multiple paths between a source and a destination, and our focus is to measure the latency difference between these load balanced paths. We refer to the problem of load balanced path having different latencies as latency imbalance. Since we use public cloud as vantage points for our experiments, this paper provides a cloud-centric view. We'll start with a very simple example. Router A has two alternate paths of equal hop count to router B through routers 1 and 4. Router A then chooses one of the alternate paths and sends the packet to router B. From this example, we can see that using LB path is more reliable to router failure and better utilizes network resources. About 40% of source destination pairs in the internet were found to have LB path in between. LB paths are generally selected to have equal path costs, measured by hop count, bandwidth, or other performance metrics. Routers select LB path as if it makes no difference using one than another. However, as there is no universal definition for path cost, and equal path cost does not necessarily mean equal performance. So LB path could differ significantly in path performance. Using latency as a metric for path performance, our work answers two key questions. First, how significant is the latency imbalance? What is the impact of latency imbalance on applications? The first question was studied back in 2007. Only 2% of source destination pairs were found to have significant latency imbalance. As 2% was not enough to raise concerns, this problem became underexplored, and most research focused on topology difference. In 2019, we measured latency imbalance from a cloud-centric view, including measurements from the cloud to the public internet and between data centers in the cloud. We have several findings. First, about 16% of pairs have significant latency imbalance. And the worst data center has latency imbalance greater than or equal to 20 milliseconds to 60% of addresses. Moreover, we found 8 data center pairs have very large latency imbalance, greater than 40 milliseconds. For the second question, we studied its impact on 3 applications. The first one is latency-sensitive applications like voice over IP. With all other conditions being equal, using a lower latency path could result in better quality of experience. This impact will become more prominent in the era of 5G when the last mile latency is less than 1 millisecond, and the latency bottleneck will be shifted to the internet. Our evaluation shows that 14% of VoIP calls between certain countries like US and China would have better call quality. The second application is delay-based geolocation. Important to create IP geolocation database widely used in advertising and geographic access control. To understand how delay-based geolocation works, let's look at an example. We have 3 landmarks with known locations here, and our goal is to geolocate the target. Each landmark will first measure the latency from itself to the target, and then use the measured latency to estimate the distance in kilometers to the target. When latency imbalance is large, it's likely that we'll get a higher latency and thus have overestimated distance. A lower latency path in this application means better distance estimation. We found that ping could easily overestimate latency. Our experimental results show that geolocation accuracy could be improved up to 40% for 20% of addresses when used in some cloud-based applications like cloud-enabled IoT. The third application is network clock synchronization, more specifically the NTP protocol used to synchronize global internet devices. NTP accuracy is affected by path asymmetry. That is, the latency from A to B is not equal to the latency from B to A. Measuring latency imbalance gives us the ability to choose more symmetric paths, resulting in less synchronization error. Our evaluation showed that synchronization error could be reduced by as much as 27 milliseconds. Latency imbalance is also important to other applications, like latency imbalance could serve as a new metric to describe latency characteristics. This is very important to measurement studies that characterize path latency and also very important to emergent data-driven systems relying on latency for decision making. Due to time limit, we're not going into experimental details. So after talking about the background, major results, and the motivations, we'll next move to the challenges and measurement methodology. We start with the definition of latency imbalance, which is the difference between the highest and lowest path latencies. The forward paths are from the source to the destination, and the return paths are from the destination back to the source. There are two types of latency imbalance, one-way and two-way. One-way imbalance only occurs on the forward path, while the two-way imbalance occurs both on the forward path and return path. Both one-way and two-way imbalance can be accurately measured, and they affect different types of applications. However, as it is much easier to discover forward path than return path using TTL limited probes, we can understand the causes for one-way imbalance with detailed path analysis. In this work, we set our goal to measure one-way imbalance at the internet scale. To measure one-way imbalance, our first challenge is how to do it from a single end. We send two probes from the prober to the target and obtains two round-trip time samples, round-trip time 1 and round-trip time 2. However, we know the one-way imbalance is equal to F1 minus F2, which is the difference between the forward path latencies. We find that F1 minus F2 can be equal to round-trip time 1 minus round-trip time 2 if R1 is equal to R2. This implies that we need probes to take different forward paths and the same return path. On the forward direction, the source first sends a UDP packet to the destination. For UDP packets, load balancing is done based on port numbers. At router A1, the source and destination ports of the packet will be hashed to determine the next hop, which is router A2. The source then sends a second packet with different source and destination ports, making the second packet likely to take a different forward path to the destination. So in this example, router A1 forwards the second packet to router A3. Upon receiving UDP packets, the destination responds with ICMP packets. For ICMP packets, load balancing is done based on checksum. We manipulate all ICMP headers to have the same checksum so that all ICMP responses will take the same return path. In this way, we can measure one-way imbalance from a single end. Recall that one-way imbalance is the largest latency difference between forward paths. In other words, to measure one-way imbalance, we need to discover all forward LB paths. A Solomon approach is to enumerate all forward paths using trace route, which involves heavy communication overhead, not scalable. Our approach is based on sampling. We treat network as a black box and sample alternate paths by sending probes of different port numbers. We refer all probes with the same port number as a flow. By taking a random flow, one path will be covered. The more random flow we use, the more path will be covered. We consider the largest latency difference between covered paths as measured range. With a sufficient number of flows, the measured range will be close to the actual range. Since some uncovered paths, for example, P1 here could have very low path probability, Covering all paths may require a very large number of samples. We instead define high coverage to be the probability sum of covered paths larger than 85% and requires high coverage to be achieved at the confidence level of 95%. We find that high coverage can be achieved when using 30 samples. As we discussed, if we know the highest and lowest flow latency, we can easily calculate the measured range. However, measuring flow latency is not trivial. Round-trip time samples could fluctuate over time as shown in this figure. So a common approach is to take multiple round-trip time samples of the same flow and use the minimum one as the flow latency. However, as there are many flows, we don't want to measure latency for each flow. We resample only candidate flows with the highest and lowest latencies. As in this example, we have 6 flows, and the 4th flow has the highest round-trip time. So we only resample the 4th flow, and in this case, we get a lower flow latency because the previous sample is inflated. We thus update the flow latency and resample the next flow with the highest flow latency. This time, the new sample is higher than the old one. We thus know the old sample may not be inflated. A sample is considered not inflated if it's found not inflated for 6 consecutive resamples. Then we can find the lowest flow latency in a similar way. Now let's look at the measurement results on latency imbalance. In our experiments, we measured latency imbalance from data centers in 14 cities around the globe to 3,000,000/24 prefixes. These 3 figures show the distribution of latency imbalance by cloud providers, where the x-axis is the one-way imbalance. From these figures, we can see that latency imbalance is both significant and prevalent. Even the best data center, Google Tokyo, has latency imbalance greater than 10 milliseconds to 7% of addresses. We can also see that latency imbalance differs significantly among cloud providers. Google's data center generally has less latency imbalance than Amazon and Alibaba's data centers. We'll discuss the reason later. So why cloud providers have very different latency imbalance? To understand the causes, let's first review how internet routing works. Suppose router A in AS1 wants to send packet to router B in AS2. The packet first egresses AS1 and enters the neighbor AS. We refer the distance from router A to the first router in neighbor AS as the egress distance. Networks within the egress distance is under control of AS1, while networks beyond are public internet, which is out of control. We measured egress distance in hop count and round-trip time from each data center to 500,000 random destinations. The bottom left figure shows the median round-trip time and median hop count of egress distance by data centers. We first look at the median round-trip time and find that Google data centers have very high median latency, indicating very long egress distance, while Amazon and Alibaba's data center have very low median latency, indicating short egress distance. A long egress distance indicates that Google controls a very large portion of path to destinations, while Amazon and Alibaba don't. If we look at the median hop counts, we will see that Google's data center have very smaller hop count to neighbor ASs. Some Google's data center are only 1 hop away from the first router in the neighbor ASs, indicating that Google's private networks are visible to our probes. In summary, we propose that Google uses its private WANs for better control over path, while Amazon and Alibaba rely mostly on the public internet. To further confirm our proposition, we look at the egress distance and round-trip time from Google FinNet to 1,000 addresses. From this figure, we can see that the egress distance increases with round-trip time to destinations, and the egress distance stops increasing for some addresses when round-trip time is very large. The capped egress distance could indicate the edge of Google's private networks. In summary, Google outperforms Amazon and Alibaba in latency imbalance because it uses private WANs to transit packets close to destinations, and that Google's private WANs have well-balanced paths. After studying the imbalance from data centers to the public internet, we now look at the latency imbalance between data centers. So inter-data center WANs serve many latency-sensitive traffic between data centers. It's important to understand the latency imbalance between data centers. The bottom left figure shows the one-way imbalance between data centers from the same cloud provider. Google generally has less intra-cloud latency imbalance as its private WANs have well-balanced paths. There are two Microsoft data center pairs have one-way imbalance greater than 30 milliseconds. With detailed path analysis, we find that these two data center pairs have load balanced paths of very different lengths, and the long distance paths in between are poorly balanced. This figure shows the latency imbalance between data centers belonging to different cloud providers. Google has less inter-cloud latency imbalance due to the same reason that it has well-balanced paths in its private WANs. But eight pairs involving Alibaba's data center have very large one-way imbalance, no less than 40 milliseconds. With detailed path analysis, we find that the causes for these outliers are twofold. First, the inter-AS path between intermediate ASCs are imbalanced. And second, the intra-AS paths in the neighbor AS of Alibaba's data centers are also imbalanced. In summary, in this talk, we have discussed three major points. First, latency imbalance can have significant impacts on application performance. Second, we developed a methodology of efficiently measuring latency imbalance at scale. And last, we have shown the memory results to demonstrate that latency imbalance is significant both from the cloud to public internet and between data centers in the cloud. That's all for my talk. Thank you for listening.